Good morning, everyone. My name is Lipeke Pugwan, and I would like to welcome you to the HPC technology track or session. My role this morning is so simple. I'm here to introduce and welcome our speakers. Please note this session is running in parallel with other sessions on the conference program. If this is not the session you are intending to attend, I guess you are most welcome to leave and join the other Zoom meeting. But I would like to encourage you to stay and get ready for the most interesting discussions aimed to address issues relating to HPC storage and IOS from our brilliant speakers with the most interesting topics. Before we can start, you are advised to raise a question to the speaker on the Q&A platform during the session, and the speaker will answer all the questions at the end of the presentation. And each speaker will present for 20 minutes, and I have 10 minutes of responding to all questions. Well, this I think should be familiar by now. The time is now 1 minute past 11. Our first topic raises an interesting question of why store your data in the cloud when you can use a cloud. And the topic is titled Calabash, why you store your data in a cloud when you can use a cloud. Ladies and gentlemen, let us welcome Simon Redley, a lead for scientific computing from South African Radio Astronomy Observatory, RAO, to take us through the presentation. Simon, you are welcome to start.
Thanks very much, Lipeke. Let me just share quickly. Great. So, good morning, everyone. My name is Simon Ratcliffe. I'm sort of wearing two hats this morning. I am part of the SARAO, South African Radio Astronomy Observatory, and also part of a company called Solar Storage Systems. And hopefully the title will make some sense as we progress, but it's really a look at both the role of government-funded research in innovation and a new product that is sort of the fruits of that, that partnership. And I'm going to start with a little digression on radio astronomy and why we're doing it and why that leads to some innovation. And then I'll talk a little bit about this new product and its hopeful applicability and interest to this community. So hopefully everyone on the call has an idea of what that is. That's the Meerkat radio telescope, which is in the Karoo, pretty much in the middle of nowhere. We have to build it in a very remote part of the world so that we're not affected by all the things that give us our modern existence. So cars and cell phones and Bluetooth and laptops, all of these things interfere with operations of a radio telescope. So you have to build it far away in the middle of nowhere such that you can get the best possible viewing and you don't have your observations corrupted by all these influences. Now, a radio telescope looks like it's mostly composed of a lot of big dishes and lots of metal and silverworks, which is true. But if you break it down, really what a radio telescope is fundamentally a device for hopefully producing Nobel Prizes. And what it uses to do that is a whole lot of information it collects from the sky. Now, because of the way we construct these things, we're very imperfectly sampling our actual underlying input data set. So what we want to know is, what does the sky actually look like? What we get is a view of the sky corrupted with all sorts of corrupting influences. And the job of the back end of the radio telescope is to figure out, right, how do we take out all of those problematic issues? Things like each antenna has a variable gain. We look through different patches of the sky. They all have different cable lengths. We have all these sources of uncertainty and error that we need to remove. And there's this magic box that we build that consumes petabytes of data and data storage, uses petaflops worth of compute, megawatts to drive that, and hopefully not too many gigadollars to build it. But that's the box that goes and churns away in this data and hopefully gives you your sort of actionable science out the end. So for Meerkat, this was sort of our rough spec sheet of what we needed to achieve. This is about 2017 timescale or so, when this was what was needed to be deployed. This has obviously been running in the Karoo for a couple of years now. The telescope was inaugurated in 2018 and has been very successful scientifically since then. But it's a modest ask, certainly by global HPC standards, but we still wanted more than a petaflop worth of computing and 40 pibibytes worth of storage in total. And at the time, we had a good round with the vendors, particularly in the storage side, and our budget was around the 30-odd million mark. And if we had just opened up the doors and gone straight to the vendors, we would have been in the 100+ million mark. And that really drove us towards how can we be innovative? How can we deliver this thing for cost effective and fit within our budget? And we did quite a lot on both the compute side and the storage side. Today, I'll just be really talking about the storage side and what we did there and how that was helpful in getting us to a working system in a good period of time, but within budget. And what we decided to do in the storage side was build the thing literally from the ground up, from scratch. So that meant designing our own chassis, designing our own PCBs, bending the metal, all the way up through the software stack, the control and monitoring layers, essentially top to bottom of the storage stack. We felt that doing it ourselves was the best way to bring those costs under control. So we partnered with a local company called Paralex, who are based in Cape Town, and we designed this storage chassis, which would be the building block of our overall spinning disk storage deployment. There were a couple of reasons for rolling it yourself. The question is always, why build it yourself? There are certainly many vendors who have bigger economies of scale who can build these things and should be able to build them cheaper. There are a couple of reasons we did this, one of which, interestingly enough, is a feature that doesn't typically come up, and that's we needed to hit a quite aggressive weight target for this appliance. The data center in the Karoo that's near these telescopes, I've already mentioned, we build this far away, so we're not influenced by the signals from all these man-made contrivances. But we do have a data center out there. And that data center is built underground and heavily shielded. And part of that shielding is essentially a big copper enclosing cage, serves as a Faraday cage, but that is supported on a polystyrene layer. All that boils down to is that your point loading on your racks is quite low. We can only put about 700 kilograms in a rack in that data center per rack. And so a traditional storage appliance, the steel chassis was really, really heavy. So we wanted an aluminum chassis. It was one of the design requirements. And there were a whole lot of others, like we wanted each drive to be directly connected with its, not using port multipliers. We wanted direct SATA connections to each for performance, and a range of other things. But so we embarked upon this project design phase. We built this thing. And those are the final renderings of what it ended up looking like. And we got them all delivered. And one of the things we sort of underestimated slightly, and this is the floor in the CHPC in Cape Town on the left-hand side there. One of the things we underestimated a little bit is it sounds fine on paper to order 3,000 hard drives. When they get delivered, you realize it's 3 tons worth of spinning disks sitting on the floor that you need to do something with. And not least of which is you need to unpack all of those and put screws on them and mount them in the chassis. And so installing those 6,000 screws ended up taking quite a bit more time than we'd anticipated. So that's a good lesson learned. Next time we'll ask the vendor to do that for us, at least of the drives. But there's our deployed system. So we have 55 of these storage chassis deployed, again, as I said, at the CHPC. This is using 8 terabyte drives, which obviously at the time was the biggest we could get. So the tide marches on very rapidly in the storage density space, which is very useful for us. And on top of that hardware, there is a big software stack, which is principally composed of open source components. So the main thing we use is Ceph as effectively our storage orchestration layer. And we present that to both our internal telescope users and our external science data users, principally via S3. So S3 is our transport of choice. And really that fundamentally boils down to having an HTTP style protocol is much easier to proxy and secure and firewall and manage. And we get pretty good performance from that. We typically see usage patterns in the sort of 3 to 4 gigabytes a second with the people interacting with this through a single gateway. Currently, it's reasonably full, so we have 14 pibibytes or so worth of capacity in there, and we manage that all the time. So we're at the stage now where, as big as the storage is, It's only really managing the last 9 months or so worth of data, and we have to continuously age out data from the system and stick it onto tape. So that's by way of a precursory introduction into what I'm going to talk about for the second half of this talk. And that's really this idea of what do we do with this technology and these ideas and this innovation that we build, essentially this public sector research that happens. How do we make this applicable and commercially viable as well? And so what we've done with Sorau is we formed this technology partnership between these two companies, between Solar Storage Systems and Sorau itself. So Solar provides a kind of a tech development arm in a way to Sorau. Sorau has a direct shareholding in Solar, and the idea is to have both a commercial and government sector focus. It's to get these products and ideas out to benefit the government sector effectively at cost, and to use the commercial space to drive some revenue to manage further innovation down the road. And you can see on the right-hand side there, that's one of the first projects we did. So that was a petabyte worth of storage we deployed for a company called Vumacam in Joburg. This is the storage underlying their public space camera network that they have on Joburg street poles. So that was a good example of something where we were able to offer them a very competitive price for bulk storage for video and further video analytics. So that's the rogues gallery of all the Solar people at the moment. So I'm in there myself, and this is basically a blend of current and past Sorau employees, as well as we have a bunch of other people who are working on this. And when we look at the kind of things we want to do and the kind of projects we want to undertake, really there's sort of a charter that sits underneath this and drives the ideas and what we want to achieve. And I think the first of those is obviously technology development that is relevant to what Sorau needs. It's an important part of, as we continue to build Meerkat extension, which is the next generation of the Meerkat telescope, and on into the square kilometer array, there's continuous inflection points where we need technology refreshes, we need new and innovative ways to do things. As we've seen certainly with this conference and with SC20 recently, we're again in a time of a lot of change, a lot of movement, a lot of turmoil. And I think that's very exciting over the next couple of years as we look forward to building next generation systems and compute. But to do them in the way we want to do them with the budget that we typically have, we need to bring quite a lot of innovation to bear. As an example, for our compute deployment, we ended up having to use consumer GPUs because we couldn't afford the enterprise level GPUs. And that brought with it a whole series of challenges, not least of which was the sort of cooling and management side of them. I think we did that pretty well in that of the 100+ consumer GPUs we've had deployed running for multiple years, we haven't had a single failure, which is a pretty good record, and shows that you can make consumer technology last if you do it sort of sympathetically and deploy it carefully. So in addition to being relevant to what Sorau wants, there's this idea of being beneficial to the wider government sector. And that was always one of the anticipations and aims of a project like Meerkat and the SKA, was that part of the spin-off and benefit to the country for putting this money in the first place is that we would build technology and technology competencies that could be brought to bear, particularly in the government sector. Then significant localization goes hand in hand with that. We would like to, as much as possible, spend the money in country. Clearly, when we're buying bits of silicon and we're buying bare drives, there's no local content for that. But as much as we can in terms of things like chassis and PCBs, local engineers, software stack, etc., we're able to bring a significant component of localization to this. And then finally, a supportable commercial case. It's not completely critical that these products are able to go out into the market and make money, but certainly if there is a commercial aspect to them, that then helps the whole stack, and it helps us fund then this generation and the next things that we want to do. So back to the good and why this, you might want to store your data here rather than the cloud. So this is a calabash. And if we go back to what S3 is, so S3 is supposed to be a simple storage service. And in many ways, a calabash is the ideal example of something that's S3. It's very cheap. It just grows in the ground. You can pick it up. You just leave it in the sun for a bit to cure and you can use it. It's easy to provision. You can see where they are. It's easy to budget. It's a fixed cost. It's easy to integrate into your lifestyle. You just try to strap around and walk around. And maybe that's belaboring the point a little bit too far. But I think what we thought of for this project that we're talking about now is that we wanted to get back to the roots of S3 a little bit, and how we could bring some of these aspects of it back, which I think perhaps have been lost a little bit in some of the modern cloud offerings. And to me, this is the classic example of that, not to in any way diss AWS or pick on them. All the cloud providers are exactly the same. When you look at storage from a cloud provider, the fact that your calculator has to have 10 plus decimal places, and these are actual numbers from the AWS pricing calculator, the fact that you have to understand what all these line items mean, this is fine if you've got 1 terabyte of storage, but if you've got 10 petabytes of storage, all of these numbers multiply out quite quickly and rapidly, and you really need to have a good handle on them to understand what are you actually going to pay for? What are you going to be faced with at the end of the month in terms of billing? And I think this has got quite complicated. We've seen what happens is you bring in other products and other tiers, and you have a hot tier and a cold tier and a glacial tier, etc. But all of that still muddies the waters and makes things difficult. So our product, which we are hoping to launch by mid-year, and we're busy working on, I'll show you some of the development activity, is a service we're calling Calabash Red. And the idea with this really is it's fast, secure, reliable, S3 delivered storage for 100 Rand per terabyte per month, all in. So no usage fees, no data transfer fees, no put and get fees, no complicated calculator needed to be used. That's it. You pay 100 Rand per month. You have access to a terabyte of reliable, redundant, locally hosted, onshore storage. So you're fully compliant with Poppy and other things like that. And you really can control and understand that budget. It's very straightforward. It's month to month. There's no lock-in. As you need it, you provision it, you use it. When you're done, you leave it and off you go. And I'll show you a little bit about how we're hoping to hit that price point and why we think it's a compelling service. So as I mentioned before, understanding what you're actually going to pay, a big part of that is this usage exposure. So if you're on the 0% download a month, you're really not doing much with your data. If you're using it just in a cold fashion, the cloud offerings are fairly competitive. We're still significantly cheaper than those. But as soon as you start to use your data in any significant form, particularly as you head up into the 50 plus or 100% worth of download of your data per month, the costs quickly spiral out of control. And again, this is fine if you've got a terabyte of data. If you have a petabyte of data, your bill can get quite nasty quite quickly. So how do we drive down TCO in a product like this? And there's 4 key areas that we've addressed in this. First is to use commodity disk drives, not enterprise grade. So we use basically the cheapest drives we can get. These have been getting better and better over time, but a lot of being able to use them is paying a lot of attention to vibration and cooling, which we do, as well as your software stack that sits on top of that, that's reliable enough to handle failures as and when they occur. Obviously, an open source software stack in itself generally is a good way to drive down that TCO, especially if it's packaged up nicely and presents an easy to use interface. We focus a lot on power efficiency over density. So our density numbers are not massively high, but that's because we really are driving power efficiency. And we see, especially over the 1, 2, 3 year periods, power efficiency is something that is more important than density, particularly in the South African market and the way the market's moving at the moment, where power is getting ever more expensive. And finally, that graceful failure and self-healing. So we don't need a huge staff complement to manage this product. And underneath there's sort of the stack that this is built on. Hardware-wise, we have a fundamental building block. This is the line replaceable unit of the beast. So it's a 32 terabyte building block. We use multi-gig Ethernet, so 2.5 gigabit Ethernet is a good blend of cost and power and performance, and it matches the spindle performance quite well. So we don't have an imbalance of too much network or too little network. It's kind of the Goldilocks, just in the right sweet spot. These pods can have NVMEs for index pools. We don't put them on all the building blocks, but quite a few of them. And then, as I say, vibration protection and isolation is an important part of it. There's one of our test rigs. And just to say on that our overall networking concept is 100 gig Ethernet is your handoff, and it's non-blocking all the way down to an individual spindle. We also have some embedded GPU support, which is for future products. We end up with roughly somewhere between 8 and 10 LFF per U as our density, depending exactly what configuration we put down. So it's not super dense. Obviously, you can buy 100 disk in 4U density, but there your balance of memory, network performance, and CPU performance to an individual disk is very hard and very expensive to get high enough. Whereas with these smaller building blocks, it's much easier to get a significant amount of CPU per drive. Our target is, say there's 5 watts per drive. That excludes the drive. So just in terms of the surrounding infrastructure that's needed to deliver that drive as an actual storage target. And we have to go into public beta around about Q2 next year. And finally, then looking forward, we called this one red because we thought we would have some other things. The other thing we have cooking up is Calabash Blue. So this is a sort of self-built and designed tape robotic system. So we're busy. It's one of the projects that we have underway. There, the focus of that system is very much on chain of custody and fingerprinting. So this is a long-term archival service, basically particularly for things like video evidence, where you want to store your camera footage, you want to know it's secure, it's properly checked through, there's a full chain of custody, who's touched the data, who's looked at it, what's happened to it, to get to the point where it's evidence grade. And that's a product we'll be looking at towards the end of the year. And then obviously, there's a lot of data mining that can be done with these services, and the embedded GPUs will come to bear as we look forward to mining and indexing and deduplication of data that's stored in the product. And yeah, if you're interested, please ping me, let me know. Happy to talk about all things radio astronomy, storage, working with the government, how we can do technology development for the benefit of all of us, and anything else that might come up. So yeah, please drop any questions you need, and I'm done. Thanks very much.
Okay, thank you, Simon. We have one question. Can I read it for you, or you?
I think I can question there.
Okay, let me just read. It's from Kevin Colville. It says the community drive use SMR. How does that affect performance of a Calabash?
Yeah, so that's a very good question, Kevin, and a very appropriate one at the moment. I think what we've seen is that some vendors are better than others at whether the drive you're buying actually is shingled or not. It certainly affects write performance, and it's something you have to pay careful attention to. We've been quite lucky so far that the drives that we've been using, we've been able to get away with not using shingled drives. And the roadmaps we have at the moment indicate that certainly this current red deployment that we're planning to do, the 16 terabyte drives we're going to use, is we won't have to deal with that. They won't be shingled drives. But it's something that's getting harder and harder to tell. And we always ask the vendors, please don't obfuscate the fact that your drive is being built in a certain way. Because, as you rightly say, it can lead to very significant degradation in write performance if it's not something you've taken into account. So far, we'll be okay. Looking ahead to the next couple of years, we have to continue to pay attention to it. I see there's also another question from Eugene. Just
Eugene, yes. Yeah, Eugene, I don't know if it's a question or comment, but let me just read it for you. It says, Calabash looks really interesting. I'm keen to follow the project. I wanted to know a little bit more about your performance experience with Ceph S3. You mentioned that you are seeing around 3 gig per second of throughput, unless I heard it incorrectly. Can you potentially speak to the scale of use? How many clients are typically connected at one time? Are you hosting Rados gateway service on the machines with higher CPU core count? If not, are you satisfied with the performance you are getting with the 4 core machines? I don't have much experience with the Rados gateway myself. I'm curious about its use, but it's my understanding that you would be quite limited with a few cores on your nodes, especially if the data is very fragmented. Although I suppose that the 25 gig network would put some limits on there anyway. It all comes down to data access patterns.
Yeah, thanks very much. It's a good mix of questions there. Yeah, we typically see 3 to 4 gigabytes worth or gigabits worth per second worth of performance out of those gateways. Those particular numbers come from, we use 3 gateways behind a proxy for that. The proxy itself has a 100 gig interface. The gateways are not on particularly fast and high performance machines. We for the deployment that was evidenced there, we weren't using erasure coding. So that's just simple data replication. That obviously helps the performance of your gateway because you're not trying to assemble so many fragments at a time. For the Calabash Red product, that will be, so we're probably targeting something like 7.2 erasure coding. We're still busy working on some testing on that, where then your core count on your gateway is a bit more important. For the Sorrel deployment as well, we're a little hamstrung by the 25 gig internal. So all the storage nodes themselves are 25 gigabits. And with 48 OSDs per node, that 25 gig can be a limiting factor. Obviously, we have a lot of spindles, which gives us a lot of parallelism, but there are times where that starts to run into trouble. I think as well, we're seeing that there's improved performance in the gateway coming, and with newer versions of Ceph, we're using Luminous still in that deployment, and I think we could probably bump up our performance a fair bit if we needed to. That all being said, we're still basically have some headroom in those numbers. We just typically don't have that many clients. So we normally have 1 or 2 clients doing writes, and then in the low tens, maybe 10 or 15 doing reads. And given the various sources those reads come from, quite a few of them come from the general public internet, obviously come relatively slowly. There are some internal customers, but a lot of those end up being connected on 10 gigs. So there's a bit of a bottleneck there. So all being said, I think you can get pretty good performance out of Radis, and I think the benefits of using S3 for delivering data to users has been very beneficial for us, and we haven't had any performance complaints as long as you put the indexing on an NVMe. So that's the most important and critical part by far, is to put those S3 index pools ideally in your mons. We found that's the best place to stick them, and as I say, make them NVMe backed.
Okay, thank you once again, Simon. Well,
Sure.
there's no questions from the Q&A, and the time is 11:27. Ladies and gentlemen, we still have, I think, probably 3 minutes. If you have comments or questions, you can still post them or raise them here. If there's no question, then we will wait until 11:30 for our next topic. Well, the time now is 11:29, and we are now moving to the next topic. I think we can agree that performance is a critical factor when you are aiming to transfer a large of data set across the networks. But I would like to leave this argument to our next speaker to discuss it with us. The next topic is titled Sunren Data Transfer Pilot Service and Performance Enhancement Response Team Update. Ladies and gentlemen, let us welcome Cassandra Pillay from South African National Research Network, Sunren, one of our key component of NICIS. She's coordinating the performance assessment and response team initiative at Sunrun, which is focusing on Sunrun data transfer pilot service, helping South African researchers to move their data set between sites and faster. So Cassandra, the platform is all yours. You can take us through the presentation. Thank you.
Thank you so much. Morning, everyone. So I'd like to give you an update on the Sunrun Data Transfer Pilot Service and the Performance Enhancement Response Team initiative that we are running within NICIs. So to give you an overview of my presentation, I'll just explain what the PERT concept is and the services that we are offering within NICIs. I'll touch on the large data transfer challenge, which is one of the main problems that we are solving through this initiative. The Science DMZ network architecture, which is being implemented to solve the large data transfer challenge. Some of the existing use cases that we have solved through the service, and then how to access and make use of this service. So for those of you who are not familiar with the term Performance Enhancement Response Team, is also known as PERT, and provides an investigation and consulting service to academic and research users on their network performance issues. And this is a term that was coined by GIANT, which is the European NREN Consortium. And we are basically trying to tackle these network performance issues on the Sunrun network to help you move your data faster. Within the NICI's PERT service offering, we have broken this down into two main service offerings. The first one being assistance with large data transfers. And this is between the NICI's resources, that is to and from CHPC and DURISA, between the NICI's beneficiary institutions, and between beneficiary institutions and their international partners. So as one part of this service, we are offering consultation, which is basically advice and assistance to facilitate easy transfer of your data sets. And this is done through the implementation of the Science DMZ architecture and data transfer nodes, which I'll expand on a bit later, and with the help of the National Persona Monitoring Toolkit that we have in order to monitor the Sunrun network. And what we've seen is that at times these requests that we have from researchers are not about data transfer alone. There's often a storage and compute component to it as well. And this is where we involve the extended PERT team within NICIs to help tackle these specific use cases and tailor a solution for these use cases. The second part of the assistance with large data transfers is making use of the data transfer pilot service, which we have implemented. And this basically consists of NICI's data transfer node infrastructure. The second main PERT service that is offered is investigating specific cases of poor network performance, which is related to your specific project that is being implemented. So we'll do our best to attempt to investigate and resolve these issues, as well as proactively trying to improve network performance using the Persona Network Monitoring Toolkit and a national dashboard that we have implemented. And these poor network performance issues are specifically from one NICI's beneficiary institution to another, but can be locally and internationally to the research partners as well, and to and from CHPC and DURISA over the Sunrun network. So one of the main problems that we're trying to solve is the large data transfer problem, because we often find that moving large amounts of data is a challenge, and it can be slow and frustrating to move these large quantities of data over a general purpose computer network. In most cases, campus networks are optimized for business operations and not really tailored for data-intensive applications. And that's where we step in to try and resolve some of these issues. So key components of the science DMZ architecture that we've implemented at specific sites in this country to solve these issues are a dedicated network enclave, dedicated software and systems for data transfer, integrated performance measurement and monitoring through the use of persona, and tailored performance security. This is an example of the science DMZ design pattern that we've implemented at various points of the country. And what we're trying to do here is that instead of moving a large amount of data directly into the researcher's campus network, which will have to bypass the firewall at the local LAN and slow down data transfer movement, we have implemented this portion in green close to certain campus networks. And the idea is to create a high bandwidth, a clean high bandwidth path, and land the data over a long haul route into a high performance data transfer node. And this will allow for the fastest movement of data possible. And once the data is as close to the campus network or the final point or final destination that it needs to sit in, it can then move over a shorter route into the campus LAN as necessary. But I've learned over engaging with many researchers that they often are overwhelmed with too many of the technical details. I now am not going into this into too much detail until the point in time where we have a specific use case and need to tackle this in more detail. But for your information, at the moment, most of our data transfer nodes are situated at Cape Town and in Gauteng, between Johannesburg and Pretoria, because based on our user engagement, we have found out that majority of the large data transfer users within the country seem to be sitting in these areas. We will have to go out and do this science engagement process again to see whether there's any growth in other areas in the country, and we will then move towards placing data transfer nodes in different areas in the country going forward. But for now, the NICI's infrastructure for large data transfer is summarized in this table. So at the CHPC or at CSR Rosebank in Cape Town, we have 4 data transfer nodes at the moment. This is on the Lingao, Legacy, and AceLab and CERN infrastructure. And we also have 4 data transfer nodes, which was part of the initial SANRIN data transfer pilot project, 2 sitting at Pretoria and 1 at WITS and 1 at the Terraco data center in Cape Town. Each of these have varying amounts of storage, ranging from 13 terabytes to the Lingao and Legacy clusters and the CERN infrastructure, which is 700 terabytes at the moment and 3 petabytes to come. Well, also 4 petabytes at the Lingao and Legacy clusters. So in order to engage, or while we are implementing a solution for the researchers, there are 4 elements that make up the science DMZ design pattern, and one being the engagement with the researchers itself to understand what their needs are. We then offer these dedicated systems for data transfer in the form of data transfer nodes, the specialized network architecture which is implemented, as well as performance testing and measurement via Persona. And the Science DMZ design pattern was created by the Energy Sciences Network in the US, and we are mimicking their design pattern here in South Africa. Some of the use cases that we've had and that we've tackled as the PERT team and provided solutions for these is the Global Climate Institute, which is located at Wits University. And they needed to retrieve multi-image spectral radiometer data sets. And we helped them by retrieving these data sets from NASA to a local user's desktop at Wits University. And our input here was modifying and creating some custom scripts for the researcher, which automated some parallel downloads from the NASA archives to the Wits researcher. And we worked quite closely with him, so he's now able to do these transfers or conduct these transfers himself. The initial test showed a speed reduction from about 6 hours to 6 minutes for him to retrieve his data. And the data sets are downloaded weekly from about 10 gigabytes to 100 gigabyte data sets. And since the pilot has began, they've now downloaded and retrieved about 3 terabytes of data sets. And these are used by the Global Change Institute for varying research needs, such as climate modeling to vegetation time series analysis. A second use case was at the CSIR, where CSIR land satellites generated about 40 terabytes of raw data. It was then sent over to the CHPC in 1 terabyte chunks for processing. And the processing data resulted in 4 terabyte chunks of data, which was then transferred back to the CSR, resulting in 160 terabytes of output data. The third use case, which is also with the CSR Earth observation team, had an element in it where we worked with Amazon Web Services and basically implemented a trial for the compute and storage portion of this workflow. The workflow consisted of 3 parts, the one being the data transfer movement from the European satellites, the EUMETSAT European satellites. It was then transferred over the Sandrin network to Pretoria at the CSR DTN. At the CSR DTN, we did filtering of this data and then moved these data sets for compute and storage into the AWS cloud on the trial that was given to us. This is an overview of the technical solution that was implemented. So basically, the European satellite data from up above is streamed to the terrestrial server within Europe. The data was then transferred over the Sandrin network by our network engineers, enabling multicast configuration on the network. We were then able to access these data sets that are retrieved daily over the network to Pretoria in the Sandrin CSR data transfer node. And then once this data was decrypted and filtered, it was then passed over to the Amazon Web Services trial, where we processed these data streams and stored them and set up a data retrieval and visualization system. So this was very successful. However, we are now trying to move this storage and workload into the CHPC ACE labs for processing to be able to compare the 2 solutions and costs involved as well. So upcoming steps for the PERT team is our implementation of 100 gigabit per second data transfer and persona nodes. So the timelines for this is that we should see this sometime next year. We are busy speccing this hardware at the moment, and then we'll do some research with the end users to see where the best place to place these nodes will be in the country. We are also investigating the use of the new iRODS Globus connector that has been made available. And this will be quite useful in integrating Dirisa services with our current data transfer nodes. So are you a candidate for a service like this? Are you moving gigabytes or terabytes of data for your research, or do you want or need to? Do you make use of international or national data sets? And can you transfer these data sets fast enough, or are you still shipping disks? So if any of these questions are in line with what you are working on, please reach out to us to see if we can assist in any way. So any questions, our contact details are pert@sanren.ac.za. And there's also more information on the Sanren website under services and PERT. The next steps to access the service is that we'll typically send you a questionnaire to find out a little bit more about your research. And then we'll follow up with a face-to-face meeting to learn more about the specific project at hand. Thank you. And any questions?
No questions from the Q&A.
Are you welcome to send me with any questions also if you think of something at this stage.
Okay, there's no questions yet as well. Ladies and gentlemen, I don't know if we should wait for this 10 minutes because we will be breaking at 12 for 15 minutes to join the next session at 12:15. And the next session will also use the same room. So we just need to break for a tea for now. Then if there's no question, then I think we can say we have a early break and then come back at 12:15 to join the next session.
Hello, everybody. My name's Jay Lofstead. I'm at Sandia National Laboratories in Albuquerque, New Mexico, in the United States. I'll be your session chair for this next session. This session contains 2 talks. We're going to look more at the storage software layer in this session. The first talk is from Professor Michael Kuhn from Otto von Guericke University in Germany, and he's going to tell us about his configurable storage infrastructure that he uses for research purposes and potentially for some production use as well.
Hello everyone, my name is Michael Kuhn and I'm a junior professor for parallel computing and I/O at Otto von Guericke University Magdeburg. Today I would like to talk a bit about how we're combining different storage technologies to build a new kind of storage system. And to do this, I'd like to first start with a brief introduction so we're all on the same page. Then I'll talk a bit about what we call coupled storage systems, and then I'll finish with a short conclusion. So let me start by emphasizing how important I/O actually is. When people look at performance of HPC jobs, they often only look at computation, but without being able to efficiently perform I/O, applications wouldn't be able to frequently write checkpoints for crash recovery purposes or their output actually. And since I/O is often still done synchronously, it also blocks computation, so it has another influence on overall performance. And it doesn't stop at the applications. There are also pre- and post-processing tasks that scientists want to perform on their data. They use tools and frameworks to extract knowledge from the data that their applications have produced. Data management is another important factor since the sheer amount of data that we produce nowadays is becoming hard to handle. On the right side, you can see a prototypical HPC system with compute nodes at the top, a network in the middle, and then a file system that is separated into metadata and data servers. This will become important later on. And I want you to think about that there's more to I/O than throughput and latency. So how fast we're able to send data through the network here. Scientists are not interested in this. They're interested in solving a scientific problem, and they want to find interesting data points in their data. And having to search through all of the data is becoming a bottleneck very fast. So like I already mentioned, the amount of data we write is in the hundreds of petabytes for larger sites and throughputs of multiple terabytes per second. What's often used for scientific applications are so-called self-describing data formats. I will abbreviate them as SDDFs in the talk. And they're very useful because you can take such a self-describing file and give it to another scientist, and they don't have to know how your application wrote the data or what the different fields mean, because all this information will be encoded within the file itself. And it looks like this. We have a traditional file system that manages directories of folders and files, and these have metadata, so ownership, timestamps, stuff like this. This is managed by the file system's metadata servers. Within the self-describing file, we have file metadata. So this is an example of HDF5. We have groups and we have datasets, and we can have annotations called attributes for them. So within the file, we actually have something that looks like a file system itself, and this is done with the file metadata, and then the datasets are the actual file data. If we look at these parallel applications, what is very nice for us as storage system architects is that the parallel applications typically only interface directly with the underlying self-describing data format libraries, be it netcdf or HDF5 or ADIOS. A problem that we have is that the structural information, so that this is a matrix of double values, for instance, that we have in the parallel application and also in the next layer in the SDDF, is lost as we transfer it through these layers. So we have netcdf here, this stores the data using HD5. This then transfers the data to MPIO, which only knows about elements, so it would still know that this is a stream of doubles. But once MPIO transfers it to the file system, in this case Lustre, is just a stream of bytes, and Lustre doesn't know how the file, or the self-describing file looks inside. And this then stores it on block storage, and then it's still only bytes. So we have several problems. These are mostly due to POSIX. POSIX prescribes that this is a byte stream down here, and there are also problems regarding the consistency and coherence semantics that I'll touch on later. So let me talk about what we call coupled storage systems. Let's look at this picture again for the format, and what we can see here, we have two types of metadata. We have the file system metadata and the file metadata. And the problem is that in current storage systems, this metadata is weakly handled, as we call it. So the file system metadata is managed by the file system. It's put on files in the file system's metadata servers, which are typically equipped with SSDs or other fast storage devices. The file metadata, since it's stored in the file itself, looks to the file system just like normal data. So the file metadata is actually stored on data servers. They're often optimized for streaming I/O, so huge accesses, but metadata accesses are often very small in nature and randomly distributed across the file. The file data itself is handled very well by the data servers. And if we want to access, let's say, a single bit of data back here, we have to look at the file system metadata, find out where the file is actually located. Then we have to read parts of the file from the data servers to get access to the file metadata, and then we can finally get access to the file data. And all these steps have to be performed sequentially, since they're dependent on each other. What we're working with is a storage framework called Julia. It is very flexible. It contains some building blocks that you need for all storage systems, like backends, object storage, key value storage, databases. And we started this project to be able to rapidly prototype new ideas and to also evaluate them, to figure out fast whether it makes sense to continue in a certain direction. It's completely open source. It's available at GitHub. So if you want, you can take a look there. It completely runs in user space. It only has a few dependencies. It has quite a few optional dependencies, but they're not strictly required. We went that route because kernel code is very complex to write and also very hard to maintain. Having it run completely in user space also makes it possible to easily use it on existing systems. So we don't need root access or anything else. We can just start it as a normal job on the system. And we already have support for quite a few different I/O interfaces, like I already mentioned, object stores, key value stores, and databases. And on a higher level, we have support for HDF5, for RDS2, and an in-progress work on MPIO. And within the Cosmos project, we're using Julia to rethink architectures of storage systems, so how they could look like in future systems. Basically, what we're doing is to introduce what we call global metadata management. So we have these two different kinds of metadata, the file system metadata and the file metadata, and we want the storage system to handle both of them. So what we do is we couple the storage system and the self-describing data formats very closely, so there's not this layered approach anymore, but the storage system actually understands what's going on inside these data formats. This allows us to handle both types of metadata very efficiently using databases and key value stores, and also gives the storage system access to some internal structural information that we want to use in the future to make further optimizations. What we're also working on is a so-called data analysis interface that allows us some new approaches for data management. So currently, if you're looking at a bunch of different HDF5 or RDS files, there's not really a unified way to query file metadata across multiple files. So for instance, a scientist would like to say or query something like the average temperature over the last 12 months for all my experiments. But currently this requires opening all the files and executing this query, which then in turn might result in the library and the file system to have to scan all the data inside of them. So what we're doing is we want applications to continue using the self-describing data format APIs. We don't want to introduce new APIs there. So we have an existing HDF5 Vol plugin and an Adios 2 engine that allows us to do this. We have modified them or adapted them so they make use of Julia's object client, key value client, and database client. And these offer specialized interfaces for the object client, for instance, is well suited for big chunks of data, and the key value and database clients are well suited for metadata. So since we were using the existing APIs, this is completely backwards compatible. We can run existing applications without any changes on top of our modified plugins or engines. We're planning to offer optional interface extensions so we can play around with the I/O semantics and also offer some hints, but this is not necessary. And then on the other side of the picture, you see the data analysis interface. This is then used by pre- and post-processing tools and can query the object, key value, and database clients directly. So we don't need to go through this SDDF API anymore. And you'll see later why this promises quite some improvements. So let's look at the other side of the picture. We already have seen the clients that the SDDF APIs use to communicate with Julia. The backends are responsible for actually storing and handling the data. So a client is always coupled with backend, so the object client talks to the object backend. And what you can see here again is the separation into file system metadata, and file data. And this right part here makes up such a self-describing file. So what's possible with this kind of architecture is that the SDDFs can choose how to map the different types of metadata and data to our backends. We have object backends that can store data on HDDs, on SSDs, on NVRAM, also in the cloud, and we have backends for key value storage and database storage. And depending on what the libraries require, they can put, for instance, file metadata into a database and file system metadata into key value store. It really depends on what the format requires. Adios, for instance, very flat hierarchy. HD5 is very nested, since you can nest groups in groups, so it looks more like a traditional file system and might require different types of database backends. So the Cosmos project started last year and will run for 3 years in total. And we want to go for a general solution that works for any kind of SDDF API. So again, we do not want to introduce a new API in a new format. We want to make use of existing ones. It's also available on the web here, so everything we produce is open source. We already have existing code for HDF5 and Adios 2. It uses key value and database backend, and we're also working, as I already mentioned, on a data analysis interface. We also want to introduce storage tiering, so the libraries will be able to specify where on which tiers to store data. So for instance, you would like to keep maybe the last 2 or 3 timestamps on the hot storage tier here in VRAM, then a couple more on an SSD, and everything that hasn't been touched in a while can be offloaded to an HDD. We also will work on I/O semantics, meaning these strict consistency and coherence requirements that come from POSIX. We've already relaxed them and we'll make it more dynamic, so libraries can actually specify which kind of semantics they require. And to give you a glimpse, at least, of what this can bring to application performance, I brought 2 results which will be published soon in a paper we've written that is going to be published at the International Conference on Computational Science and Computational Intelligence, also in December. So the first picture we see here is a comparison of the native HDF5 format against our Vol plugin that is using a key value store. And you can see the native one, these are the lower two lines here, they run, or HDF5 runs on Lustre. So this one is the number of files that can be created per second. And this is then limited by Lustre's metadata performance. So we can go up to roughly 1,000 files per second. Since our Vault plugin doesn't create traditional files anymore, but creates entries in the key value store, we can go up to 10,000, and in our what we call the unsafe configuration even higher. The safe one synchronizes each individual file creation with the backends. The unsafe one is a bit more akin to what Lustre does with the caching. So instead of waiting for a reply from the server, it actually returns control to the application as soon as the operation has been queued. So we can already see the key value stores are pretty well suited for handling metadata workloads. And the next result is a proof of concept implementation of our data analysis interface. So as a very trivial use case, we wanted to read all the attributes from an HDF5 file. If you do this with the native HDF5 format, you get roughly 5,000 operations per second. So you can read 5,000 attributes per second. And this is shown here. If we use our Julia plugin, which is very unoptimized, we get roughly 3,000 operations. So it's actually a bit slower, but we still have room for optimization there. But this is not what we actually want to achieve. And this is to be expected since we still have to pass the full HDF5 stack. Where it gets interesting is the data analysis interface get. So each attribute we get directly from the key value store via our data analysis interface. So we get up to 10,000 operations per second. But where it gets really interesting is the iterate method. So the data analysis interface can access the key value store directly and can iterate efficiently over all key value pairs. And then we suddenly get 120,000 operations per second. So this is a speed up of roughly 20 or more. And this means that it's actually feasible to go through all the attributes in all the HDF5 files we have produced in an experiment and query something there. So let me come to the conclusion. As we've seen, existing storage systems, since they often are based on POSIX, are not really suited anymore for today's requirements. We have structural information in self-describing data formats, which is very useful and should be kept, but we are not able to make use of this structural information in the storage system since it's converted to a stream of bytes. And this is something we are working on. Another point is metadata performance can be very limiting since POSIX file systems have been designed decades ago and they weren't architected to handle the amount of files we have today. So there are millions, billions of files. And what we do in Cosmos in the Julia project is to use existing database and key value technologies to handle the metadata problem and the global metadata management to enable new data analysis approaches by being able to carry over the structural information into the storage system so we can use it for more intelligent decisions. As I already mentioned, we will focus on the metadata management problems first, but we will also tackle other problems like the storage selection, the tiering process I already mentioned, since future storage systems are bound to include more storage tiers and VRAM is upcoming. There are already SSDs and HDDs, and this is only going to increase. So we want to handle this, and we also will look at adaptable I/O semantics. So different libraries like HDF5 and ADIOS, but also others, can specify exactly which kind of semantics and requirements they have for the storage system. And then the storage system can actually adapt to the libraries and applications requirements instead of the other way around. Thank you very much for listening, and I hope we have an interesting discussion round. Thank you.
All right, thank you, Michael. That was a very interesting presentation. We don't have any questions yet in the Q&A, but I have some myself, so we can get this started. the first question I would ask is, if I am an application writer and I have a particular kind of data I need to store and I have my own custom file format, what is the level of effort and the kinds of things that I have to consider when writing one of the plugins to work with this system?
So it really depends on the library and the format itself. So HDF5 has a very clear interface with this vol interface, and that was relatively easy, at least, to get a proof of concept version running. Adios was a bit more complicated, if I remember correctly, because this engine concept, well, I have to admit we started a bit early, so the engine concept wasn't fleshed out completely. But in the end, these interfaces are designed to be as easy as possible. So you have some basic operations like creating, writing, reading from objects, and so on. So we have a few different proof of concept implementations. They're all not overly long, like a small fuse POSIX file system that makes use of the key value store and so on. Yeah, I hope this answers it somehow. It really depends on how complex your format is.
Okay. There's actually a question coming from the audience that we'll dive a little bit deeper into this. So the question from Charles Crosby is, are there serious difficulties of getting this to work with NetCDF? So in kind of a more of a concrete example, what would be the things to make this work for NetCDF?
We haven't tried NetCDF yet, to be honest. I think the main problem was that our initial HDF5 Volt plugin that used the key value store was very basic. So we only supported datasets and groups, I guess, and attributes. And I think NetCDF makes heavy use of links, so we couldn't do that. But the new one that is based on the database client should be able to do it, at least. We haven't tried it yet. So the problem is mostly what kind of HDF5 functionality NetCDF requires. And then this should also work transparently, actually, if our HDF5 plugin can do it. But the database one is pretty robust, actually. We have ENSO, a real application running on top of it, and the next step would be to try something with NetCDF.
Okay, so for the database plugins, what database engines are you supporting?
For the database, we currently have a very rough in-memory one. We have SQLite support. We have MySQL support, which covers both MySQL and MariaDB. We're thinking about Postgres, and we currently have a student that is investigating more or less only HDF5, whether it would make sense to have something maybe like a graph database, because it's very nested. So like I mentioned in the talk, you can have groups inside of groups to investigate something like this. But currently it's on the database side, it's only relational databases, and on the key value side, obviously key value. And there we have quite a few covered, like LevelDB, RocksDB, LMDB, yeah, quite a few.
Okay, all right. So kind of in a related area is, how does this compare to something like Deos?
I think the basic ideas are very similar, actually. The goals are a bit different, I would say. Deos is really production quality, I would say. We're, at least from the Julia side, we see this as a framework that others should be able to use to plug together whatever they want to try out, really. And our first real bigger proof of concept is the Cosmos project. So the targets are a bit different. We want to use this heavily in research, obviously, but also for teaching. Because what we've seen in the past is, if you give someone a project as complex as Lustre or DAOs, and you want to have them add some small functionality or make some changes, then they use up maybe 3 of the 6 months that they have for the project, just getting it to run and getting familiar with the system. And we want to improve in this area so they can start faster and try out some new things easier.
Okay. All right. So since this is doing a key value kind of interface, is there an analogy with other NoSQL databases or key value data stores that we should pay attention to as well? Or is this really using that kind of technology as just in a kind of a new structured, as initially a research vehicle and then potentially a production vehicle later?
So before we refactored it to be a strict key value interface, I was actually using MongoDB exclusively, which is a document store, I guess, which was nice because you have indexes and so on. I think there's quite a few things that the file system people or we could learn from database people regarding indices and being able to query our metadata, especially more efficiently. And that was one of the reasons we started going in this direction, trying to integrate existing databases into file systems. And yeah, in my opinion, it seems to be worth it. Like I said, we also have this small fuse proof of concept thing, and it also uses key value stores. And you can handle a lot of storage workloads using existing databases. There's not really a reason to invent something new.
Are the overheads related to using the database kind of back end? Is that in terms of storage space? Because that's been at least an anecdotal, if not a documented challenge that people have had with trying to use database technology for HPC kind of workloads. Are you seeing that this is in a reasonable level? Because I know the things that I've done, I see it as actually a pretty reasonable overhead.
So far we have obviously not done really large tests, but we're keeping it strictly to the metadata and try to keep the amount in a reasonable range, let's say. I think somewhere we mentioned 5% of the overall volume is probably metadata. And once we approach several terabytes and petabytes of data, that might be a challenge, that's true. But yes, since we only, at least for now, keep the metadata in there, it's not a problem at the moment. For the Adios 2 engine, we also have the possibility, or at least are currently working on the possibility, to using this data analysis interface, so developers can specify metrics that they want to store in the database in addition, like the averages or min and max values. So if you store too many of those in the database, obviously they will also be overwhelmed. But so far, especially for the key value stores, that didn't seem to be a problem. We haven't done much larger tests with the SQL ones so far.
Okay. One last question that's purely personal is, have you done any IO 500 tests using your system yet?
No, not yet.
No. Okay.
I was thinking about it. The question is probably which interface would be best suited for that.
Yeah.
That also has a few backends, right? So we could have a native Julia backend, obviously. But so far we were busy with getting the HD5 and Adios ones up to speed. But it's definitely on our radar.
Okay.
Especially now that we're here at our new site, we still have to set up the clusters and so on. But once everything's sorted out, that is something that is or has been on our list already.
All righty, great. Thank you very much, and thanks for presenting and having this conversation for our Q&A here.
Thank you, and sorry again for joining late. Apparently, I used Indigo wrong and selected the wrong time zone.
Oh, you are here in plenty of time, so we're good. Thank you very much. All right. So our next speaker is going to be Andre Brinkman. He's a professor at I'm sorry, I'm blanking on the university in Mainz, but he's going to be telling us about the Gecko FS burst buffer file system.
Hello, it's a pleasure to welcome you to my presentation on Gecko FS, a burst buffer file system for HPC applications. This presentation is describing joint work with Tony Cortés, Alberto Miranda, Ramon Nu from the Barcelona Supercomputing Center and with Marc-André Feef from the Johannes Gutenberg University Mainz. My name is Andre Brinkmann and I'm a professor for computer science and the head of the data center of the Johannes Gutenberg University in Mainz, Germany. Before developing a new file system, we have to ask ourselves why the existing ones are not good enough for the job. Especially, there are long-lasting file systems like GPFS or Lustre with 20 years of development background who are absolutely optimized for standard HPC workload applications with big sequential access patterns. So therefore, what has changed? First of all, HPC is now increasingly including data-driven applications. And these applications do not have these big sequential accesses, but they include many metadata operations by creating small files. They include many random accesses, and especially I/O is small. So a second point is that more and more applications are running on the HPC clusters. And these applications are competing for access to the parallel file system. And for the parallel file system, it looks like that these applications are producing random I/O, which then again interfere at the HDD backend storage. Fortunately, there is also a lot of change concerning the underlying storage technologies. So the backend storage of parallel file systems still typically relies on slow HDDs. The reason is it's just cheap. Nevertheless, there are new upcoming technologies like NVMe-based SSDs which offer much higher I/O performance and bandwidth. Their only drawback is that the price is still much higher than for magnetic disks concerning the gigabyte. Therefore, there has to be a trade-off between how you use HDDs and how you use these new storage technologies. Today, SSDs are typically provided within external burst buffer storage systems or also in node local SSDs. So this talk focuses on the usage of these new SSD technologies on node local storage, where the compute node of an HPC system also includes a small or big SSDs. Everything we are talking about today, and especially the Gecko file system, can also be completely applied on external burst buffers. Gecko FS is now providing a means to include this node local storage into the HPC storage hierarchy. First of all, a file system is created per job. This means that when a job starts on a number of compute nodes, that we aggregate all of the storage capacity within these compute nodes and build a file system on top of it. So then the input data is staged into the file system before the job starts, and after the job ends, it is staged out again to the underlying parallel file system. Therefore, our file systems only have a temporary lifetime, which might be limited by the HPC job, or in some senses, even by a campaign of different jobs. This also makes file system development simpler, because we can, for example, assume that each file system object is only accessed by a single application. Furthermore, we can also simplify capacity management, as we assume that the working dataset has to fit into the available node local storage. We furthermore simplify the development by the assumptions that we only have to support file system features which are required by most, not by all applications. This allows us to, for example, change some of the assumptions underlying POSIX, which are mostly not used by many HPC applications. On this slide, you see the standard scenario where every application is simply accessing the parallel file system. So node 1 bis 3 is occupied by application 1, and application 2 is using node 4 to node 6. All of them have node local storage in form of SSDs, but these SSDs are not used as the applications are simply accessing directly the parallel file system. So this leads to interference, and also it leads to the case that the applications can only use the performance of magnetic disk and therefore are restricted by their capabilities. This interference may look like this one. So you have a huge set of small puppies which want to play around on the ground, on the floor, and want to access the parallel file systems. Based on not ordering and not aligning their accesses, it is very difficult to keep order and therefore also to get the performance out of the magnetic disk which you want to see. GeckoFS as an ad hoc file system is now changing the situation. As we've mentioned before, the applications are starting a new GeckoFS file system instance on top of their node internal storage systems. Application 1, for example, is combining the capacities of the SSDs in the node 1, node 2, and node 3 to build a new instance of GeckoFS. Before the application now starts, it is staging in sequential accesses the data it requires into the set of nodes. Afterwards, all of the accesses of the application to storage are directly handled by the node internal storage. Therefore, there is no interference between application 1 and application 2. GeckoFS therefore simplifies the life of the underlying parallel file system. All of the accesses are now streamlined in a way that only the sequential stage in operation and sequential state out operations really hit the backend parallel file systems, and therefore all access to the parallel file systems hit their sweet spot, which means they are big and they are sequential. All of the harmful I/O patterns are now handled by GeckoFS. So creates of files or random accesses or small I/O are all handled by the node internal SSDs, so that the parallel file system can completely focus on what it has been built for. What I now want to share with you are some results which we have depicted from experiments being performed at the Mare Nostrum 4 supercomputer at the Barcelona Supercomputing Center in Spain. So Mare Nostrum has been one of the fastest supercomputers in the world when it has been deployed in 2017. It is backed by a GPFS file system with thousands of magnetic disks in the storage backend. You see here that the performance when accessing Mare Nostrum can be as high as 10 gigabytes per second from a single node and even as high as 70 gigabytes per second when being accessed by 32 nodes. So this is of course a best case result for GPFS because we have performed sequential big IOs to the file system. The tests have been performed over a period of several weeks, and we have done these individual tests at different times of the day. You see also that there are many orange dots within the graphs, which show the performance variability when accessing GPFS. Besides the very good results, GPFS shows us also very low results in some cases. So for example, for reads from a single node, the performance can drop to a little bit over 100 megabytes per second. And also when being accessed by 32 or 16 nodes, when writing data, it can also be as low as 100 megabytes per second. So you see that there's a big gap between the best case performance and the worst case performance. In contrast, the performance of GeckoFS, which is depicted by the blue points, is nearly constant over the different test runs and only depends on the number of nodes accessing the GeckoFS file system. In this case, our best case performance is nearly the same as the worst case performance, but in this case it is also still a lot slower than GPFS. The reasons are pretty simple. First of all, our GeckoFS file system has been backed by standard SATA SSDs with a peak performance of around 300 megabytes per second. Therefore, of course, accessing one SSD within the backend of GeckoFS is also limited by 300 megabytes per second. And also if you scale to 32 SSDs, we are still below 10 GB performance per second. There are 2 points in favor for GeckoFS here. First of all, more modern SSDs with an NVMe interface deliver around 3 GB per second, and we are pretty optimistic that we achieve this 10 times speed up also within such scaling experiments. Secondly, we have only used 32 nodes in this setting. The Mare Nostrum supercomputer consists of several thousand nodes, which also means that we can more or less run up to 100 instances of GeckoFS with a peak performance of 10 GB per second per instance, which definitely in this case outshines the best case performance of GPFS. I would now like to start talking about the design considerations we have used when developing GeckoFS. First of all, we decided that GeckoFS should completely run in user space, so that it is easy to install and to maintain, and that it especially does not interfere with the management of the HPC cluster in total. The second approach we have been taking is that we wanted to completely distribute the metadata management, and that we also wanted to simplify file system protocols so that we can adapt to the new situation that we are just running in the context of a single application or of a single campaign. Furthermore, we have used a very small core for GeckoFS, so that everything can be built around this small core and can be tuned for specific applications, and that GeckoFS therefore can be adapted to different requirements. Another important issue that we want to support at best all available network technologies and all available new storage technologies, so that it can be used in a huge setting of applications and scenarios. Everything we have done under the assumption that the performance should really scale linearly in the number of participating nodes within a single file system instance, and that this performance only should depend on the network interfaces used within the compute nodes and the available storage within these nodes. This slide is showing the architecture of the GeckoFS file system. In the upper half of this figure, you see a single node participating within our file system. Let us assume that the application running on this node is accessing the file system through the libc system library. We are using an interposing library and intercept all of these syscall operations going through libc. Then we decide whether it is an operation for the GeckoFS file system, and if it is an operation for the GeckoFS file system, we handle it within our GeckoFS library. So there are 2 cases. First of all, it can of course happen that this operation can be handled locally, as this local node might be the destination of the hash operation, assigning a node to this function. If it is a local operation, then the operation is simply moved forward to the GeckoFS daemon, where a RocksDB database is handling all metadata which is required on this and exactly on this node. So if data has to be written or to be read, then we are using a node local file system to simply access it. If it is a remote operation, then we are using the Mercury RPC client from the Argonne National Labs to forward this request to another node participating in our file system. So Mercury is supporting small RPCs and also parallel bulk data transfer for many network protocols, including Omnipath, InfiniBand, or Ethernet. So after forwarding these operations through Mercury, the same is being performed on the remote node, which has been performed on the local node before. A Mercury RPC server is taking the request, is then checking using the RocksDB library the node internal metadata, and might access the node local file system to store the data. The parallel file system you see on this figure is only used to stage in or stage out data at the beginning of the operations of the job, or at the end when the job is terminating. Besides that, everything is handled within node local compute and storage power. So we will now discuss the evaluation of the GeckoFS file system which in this case has been taking place on the Mogon 2 supercomputer at the Johannes Gutenberg University Mainz. Mogon 2 consists of more than 2,000 nodes and has been ranked number 65 in the world when it has been starting in 2017. We have used two different kinds of benchmark. One is MD-test, which is a metadata micro benchmark, and the second one is IOR, which is a data micro benchmark. With MDS test, we have, for example, checked the performance of file creates and of stat operations, while with IOR, we have checked the sequential data write and read performance. Typically, we have been writing 4 GB per process, while we have been running 16 processes per node, and we have used a chunk size of 512 kilobyte. So each of the nodes participating in our test has included a single SSD, which has stored metadata and data. And of course, we have scaled the performance test within the number of nodes, ranging between a single node and 512 different nodes. All operations have been performed synchronously, and we have not used any kind of caching within GeckoFS. So this slide compares the metadata performance of GeckoFS with the metadata performance of the Lastro file system. We have performed two kinds of tests. One was file create and one was file stat. Within the file create test on the left side of this slide, we have scaled the number of nodes participating in the test from 1 to 512, while on each node we have been running 16 processes. So again, we have had two kinds of tests for the file create performance. In the first kind of test, all files have been created in a single directory, while in the second kind of test, all files belonging to a single process have been created in a single directory, while no process has been accessed to the directories of another process. It is well known that Lastro benefits from this unique directory operations and has been able to scale its performance up to 30 to 40,000 operations per second. So for GeckoFS, there is no difference whether you create everything in a single directory or in a unique directory. And you see that it perfectly scales within the number of nodes, up to 30 to 40 million operations and create operations per second. This can be compared to the 30 to 40,000 operations by the Lastro file system of the Mogon cluster, therefore showing a performance increase of a factor of 1,000. The experiments at the Barcelona Supercomputing Center, shown in the beginning of this presentation, has outlined that file systems like GPFS or Lastro are able to deliver a very high sequential data write and read throughput. So which goes much beyond 100 GB per second in many settings and even peaks up to several terabytes in large-scale installations. So within this test, we have compared the performance of GeckoFS to the maximum available bandwidth of the underlying SSDs. Therefore, we have used different chunk sizes for the sequential operations, ranging between 8 kilobytes and 64 megabyte. So within the slide, you see now how the performance scales between 1 and 512 nodes. In all of these settings, we have also outlined the performance and the peak performance of the underlying SSDs. You see, for example, that up to 16 SSDs and for a chunk size of 64 megabyte, GeckoFS is able to use completely the available SSD peak performance. And that even for smaller chunk sizes, the difference between the peak performance of GeckoFS and the peak performance of the underlying SSDs is bounded by a small factor. I now want to conclude my presentation and give a short outlook on future work. First of all, GeckoFS is able today to really use node local SSDs to be included into the storage hierarchy. So in the future, we definitely want to better integrate GeckoFS into the overall HPC ecosystem. So the first step we have done into this direction is to also include it with a Slurm batch environment, so that it's now able to directly create a new file system instance when starting a new job out of Slurm. Furthermore, we are in the process of coupling GeckoFS with the Lustre hierarchical storage management component and with the quality of service features for Lustre, so that even the stage in and stage out process between GeckoFS and Lustre can be better steered. We are developing recipes which can be used within Slurm for specific application from the physics domain, from bioinformatics, and especially from machine and deep learning. From a research perspective, we are also playing around with more clearly modularizing GeckoFS so that it can be coupled directly to the requirements of different applications. If you like GeckoFS and what I've been talking about, then you can just play around with it. It is available at https://storage.bsc.es gitlab HPC GeckoFS. So I would like to thank you for your interest in GeckoFS.
All right, thank you, Andre. That was very interesting. So we have no questions officially in the question and answer or the chat, but I'll have some myself that I'd like to ask. The first one is that the other system that I've seen that's been promoted and used a lot for a burst buffer file system has been BGFS. Can you compare and contrast between the two?
Yes, so the difference between GeckoFS and BGFS, or beyond, if you see this on-demand component from BGFS, is mostly that beyond is still based on the standard file system architecture, and it's more or less bound to the POSIX semantics which underlies it. So we have compared it jointly with the Beyond team and the BGFS team from Kaiserslautern in Germany within our journal publication. And what we've seen is that BGFS is also really able to scale the sequential performance concerning the number of SSDs it uses. On the other hand, our scalability of metadata operations has been a lot higher and better than that of BGFS. So
okay.
if you really need metadata performance, then GeckoFS is nice. If you only rely on sequential performance, then don't care too much.
Okay, great. Okay, so Happy Satole is asking, how is the Lustre HSM performing? Is it the same as Robinhood?
Not really. So what we've done is jointly with DDN, we have worked on the Lustre client-side caching. And the Lustre client-side caching helps you to move data from the Lustre file system into the nodes or node local storage of compute nodes. And what we are currently working on is that we more or less want to combine and unify the namespace between the Lustre file system and our GeckoFS file system, so that if you are working on these node local SSDs with GeckoFS, that you then seamlessly see this within Lustre and can more or less automatically stage in and stage out data between both.
Okay, all right. All right, so there was an official message about what we're doing next. I just wanted to see what's going on there. So the next question that I had, since we don't have another one officially yet, is given the comparison with BGFS and the potential to use this as your only storage system, what kind of limitations or challenges do you see there, since you have this assumption of having the parallel file system kind of in the back end there?
So in principle, what GeckoFS is doing, it is working with every file system in the backend. So you've seen we have compared to GPFS, we have compared to Lustre, and of course we also work together with BGFS. So from that perspective, it's pretty similar. So what is an advantage of having this smaller GeckoFS compared to GeckoFS is also that it's easier to install, that you have less dependencies, that it runs out of the box. So from that perspective, GeckoFS do not have too many dependencies. On the other side, of course, if you want to use BGFS and Beyond together, then it can be most probably better tuned to work together with each other. So it's really a matter of taste, whether you need the performance or whether you want to have the ease of use that you only have to care about a single file system.
Okay, well, I was kind of asking a little bit of a different question, I think, and that is eliminate a different parallel file system and only use GeckoFS.
Ah, okay, sorry for that.
No problem.
Okay, then I will answer your first question. I would not yet do this. So I mentioned in the beginning of my talk that we have removed a lot of restrictions which come from POSIX. We have removed also some things concerning permission checking and so on, which all are not important within the context of these burst buffer file systems. So, and if you want to use GeckoFS as your only file system, then you have to re-implement these restrictions again, because you have to work with every application available. You have to provide security and privacy and all of that stuff. And this is what we are not tuned for. We are mostly tuned for performance. And our target area is really to work together with these file systems, either on these external burst buffers, which we are currently starting to experiment with, or directly on this node local storage.
Okay, all right. So the other major burst buffer vendor, I would say, would probably be Cray at this point. And given how their system works and it's integrated in with their scheduler and such, what would you say the comparison is between the two?
So if you talk about data warp, then it's definitely a nice solution for getting this Cray solution and work together with it. So and we even built, when extending Slurm, on their plugin for Slurm. So because they built the first plugin for Slurm to really understand how burst buffers can be integrated into the storage hierarchy. The big difference is that, of course, data warp cannot use these node local storage, which we target here. And on the other side, it's more tightly coupled to Cray. And if you just want to use out of the box external burst buffers, I think then it's easier to work together with our solution.
Okay. All right. I think that's hit all of my questions. I don't have any other in the chat or the Q&A here.
Thank you.
Give it another second here. And if not, then we will break and start again at 2 o'clock South Africa time for our afternoon session.
Thank you. Looking forward to it.
All right.
Bye-bye.
Thank you. All right. Thank you, everybody, for coming. And we will resume at 2 p.m. or 1400 South Africa time for the afternoon session.